Hello, I am Seema and welcome to part 30 of the chapter Thermodynamics. Now that we have understood about Gibbs free energy and we've related it to spontaneity of a chemical reaction, let us now try to relate it to chemical equilibrium. We know that from whatever we've studied till now, that Gibbs free energy, that is delta G, it gives us an idea, it helps us to predict the spontaneity of a process. That is, if delta G is negative, then the reaction is spontaneous. But I told you that a spontaneous process is an irreversible process. It is a process that takes place in one direction, that is from the reactants towards the product side on its own, which means that it is an irreversible process. And it also tells us about the free energy or free work of an irreversible process. That is, delta G is equal to H, delta H, which is the total change in enthalpy or energy, minus T delta S. That amount of energy which is used up to bring about the change in entropy. So that change, that amount of energy which is used up to bring about a change in entropy cannot be used for doing work. So whatever is left, the difference between the two is the energy which is free to do work, and we call it the free energy. Now if you apply this to a reversible process, that is, if we are not talking of an irreversible process and so therefore now we are not talking about spontaneity. We are just trying to relate free energy for any change, whether it is reversible or irreversible. There has to be some free energy which is available for doing work. In the case of equilibrium, which is a reversible process, how is this delta G going to be related to it? So let us see how we can do that. In thermodynamic terms, what do you call a reversible change? You remember when I told you that a reversible process may take place in minuscule steps, very small steps and many steps, and in each step the system is in thermodynamic equilibrium with the surroundings. Therefore, the change that is taking place is constantly, you have a feeling that it is constantly having the same temperature as the surroundings, or the energy change between them appears to be zero. Therefore, reversible in thermodynamic sense is a way of carrying out a process in such a way that the system is at all times in perfect equilibrium with its surroundings. Let us take a chemical equation. What do we understand by a reversible process? And what do we understand by the state which is known as the equilibrium? There are two reactants, A and B. They result in the formation of two products, C and D. The rate at which A and B are turning into C and D, at the same rate, C and D are reacting with each other to give you back A and B. So a state of equilibrium exists where it appears as if the amount of A and B and the amount or the concentrations of C and D are fixed. That state is known as a state of equilibrium. So whatever free energy change is occurring in the forward direction, the same free energy change must be occurring in the backward direction. Therefore, to the observer, it appears as if the change in free energy at equilibrium is equal to zero. While actually, we know that it is not possible for a reaction to take place if free energy change was zero. A reaction would occur only if it is feasible for the reaction to occur. But the thing here is that both the reactions, the forward and the backward reactions, are equally feasible. And at that point, a state of equilibrium exists. Now, if you remember, I told you in a previous, when we were doing states of matter, I taught you about the equilibrium state, the physical equilibrium, in terms of vapor pressure. When I told you that if you take a closed vessel and you fill it half with water, you find that vapors of water will rise into the vessel. And initially, when you check the pressure of the vessel above the empty part of the vessel, you find there is no water vapor. But slowly at that temperature, water vapor starts rising. And as it rises, the pressure inside the empty part, it increases. So it gives you the pressure, the vapor pressure of water. And at a certain temperature, at that particular temperature, after certain time, we find that now the vapor, initially the pressure kept on increasing, and then at that temperature it becomes constant. So no more vapors are adding to the empty vessel at that time. But is it actually that state? What is happening is that the number of molecules of water which are rising in the form of vapor, the same number of molecules are going down into the liquid and re-entering the liquid in the liquid state. Therefore, the vapor pressure that the instrument that is measuring the pressure, it gives you a constant reading. Therefore, you feel that the vapor pressure, the pressure at that time is constant, while actually it's a dynamic equilibrium. The number of molecules coming up in the form of water vapor is equal to the number of molecules which are re-entering water in the liquid state. Now, think of that and relate it to a chemical process. That reactants are there, products are there. The rate at which reactants are turning into products is equal to the rate of products turning into reactants. That is the state of equilibrium. The reason that I'm explaining this so much is that we have not yet started the chapter chemical equilibrium, which is the next chapter. So it is then that this would become much clearer to you. But let us proceed with this. Let us relate free energy to the equilibrium. So delta Rg, that is the free energy change in this particular reaction, would be related to the equilibrium constant. Now, what is equilibrium constant? Equilibrium constant is K, and it is represented by K, and equilibrium constant is actually in terms of concentrations, or it is in terms of pressures, partial pressures if the reactants and products are gaseous, and concentrations if they are other states also. Let us understand what Kc or equilibrium constant is in terms of concentration. The equilibrium constant K is equal to the product of the concentrations of the products divided by the product of the concentrations of the reactants. That is, concentration of C into concentration of D divided by concentration of A into concentration of B. If the reaction takes place equally on both sides, that is 50% of A and B have dissociated to give you C and D, then the concentrations of A and B and C and D at equilibrium, if it happened at 50%, would be equal, right? The concentration of C and D divided by concentration of A and B would be equal. It would be, a ratio would be 1:1. But if the reaction proceeds more towards the product side, if the reaction proceeds more towards the equilibrium exists when more of product is formed, and at that point the equilibrium state is achieved, then the concentration of products is more than the concentration of reactants. If it is more, 1/1 was 1. But if it is, let us say, 1.5/1, then the value of Kc would be more. And if the equilibrium existed more towards the reactants, that is, the equilibrium was established before half of the reaction took place, then the concentration of reactants would be more, which are in the denominator. Therefore, the value of K would be less than 1. This is just a little idea about K, which you will study in details when we do the next chapter. But let us now see how we relate delta G to it. We know at equilibrium delta G of a reaction is equal to 0. So we say if you relate it to the chemical equilibrium and the equilibrium constant, then you have to add this term, the sum of the free energy change and RT ln K. This is something that I'll explain in the next chapter now. But equilibrium constant I just explained to you. RT ln is of course the log and natural log. R is gas constant, T is temperature, and K I just explained to you. So RT, the sum of free energy and RT ln K should also be equal to 0 for a reaction at equilibrium. Now we are relating delta G to this. If you rearrange this equation, you get delta Rg, that is the free energy change of the reaction. That's why we are writing the R. Delta Rg would be equal to, take RT ln K that side, so it will be equal to minus RT ln K. Or we could say delta Rg is equal to, you change this ln to base 10. If you have to change ln, that is natural log, to base 10, you have to multiply it by 2.303. So this would be equal to minus 2.303 RT log K. Because usually when you use the solve numericals, you have the log tables. So you have to convert the natural log to log. So multiply it by 2.303 and find the value of the log. Now, free energy change we know that delta G is equal to delta H minus T delta S. So let us put this value also. Since delta G is equal to delta H minus T delta S and delta G is equal to minus RT ln K, we can equate all three. That is, delta RG is equal to delta RH negative. Now why have we put the R? Because it is the enthalpy change of the reaction, and minus means it is in the standard states. The reactants and the products are in their standard states. Minus T delta S, it means the same thing, it's only for the reaction, would be equal to minus RT ln K. Now it is this equation which becomes the most important when you are relating delta G to the equilibrium constant. Now again, for strongly endothermic reactions, and a reaction is endothermic, it means the value of delta RH would be positive. It would be highly positive. If it is largely endothermic, it means delta RH negative would be large and it would be a positive value. So we'll say for a strongly endothermic reaction, delta RH is large and it is positive. So what will happen to the value of K? If the reaction is endothermic, it means it is, if you talk of spontaneity, is it favoring the reaction? Would the reaction be favored in the forward direction? Let us for a moment forget that this is a reversible change. Imagine there are two reactions and both of them, one is where the reactants are these and the products are that, and in the other reaction the reactants are these and the products are those. Which reaction will be favored according to you? The one which is endothermic or the one which is exothermic? The one that is exothermic. That is the favored reaction. So if the reaction is endothermic, if the forward reaction is endothermic, it means that delta H for the forward reaction will be highly positive. And if it is highly positive for an endothermic reaction, the forward direction reaction will not be favored as much. Why will it not be favored? Because that is not, energetically it is not the favorable condition for delta G. Therefore, the backward reaction would be more favorable. In other words, that if you calculate the value of K, the value of K has concentrations of products upon concentration of reactants, right? The value of K is concentration of products upon concentration of reactants. And if the concentration of reactants will be more in this case, because it is endothermic in the forward direction, so A and B will not happily react, but C and D will happily react. So the concentration of A and B will actually be more than the concentration of C and D. So the value of K will become less than 1. The value of K in that case would become less than 1. You know, K, let me just write here, K is equal to concentration of C into concentration of D upon concentration of A into concentration of B, right? So when you have a reaction that is favoring the reactants, now this reaction, if it is endothermic in the forward direction, it means it is not favorable in the forward direction. So the concentration of A and B would be more. If concentration of A and B would be more, then, and since it will be much more, it is highly endothermic. Therefore, delta RH would be large and it will be positive, and therefore K would be much smaller than 1. And if the conditions were opposite, that is, if the forward reaction in the forward direction was exothermic, then it is favoring the forward direction. Then the equilibrium will exist at such a state where the concentration of C and D is more than the concentration of A and B. If it is more than the concentration of A and B, equilibrium constant would be much greater than 1. Right? So if it will be much greater than 1, so we say, so K will be, and the reaction will be unlikely to form much product. In an exothermic process in the forward direction, delta H of the reaction is large and negative. So K will be much larger than 1. And if K will be much larger than 1, it is a highly exothermic reaction which have a large K. So reaction will occur almost to completion. which means that the equilibrium will exist when a lot of product has been formed and the concentration of reactant is less. So how does Gibbs energy affect the state of equilibrium? Equilibrium is only a state where reactions are proceeding at the same rate at that point. But before the equilibrium is achieved, was the equilibrium achieved at a 50% rate? That where the reaction change that was occurring was such that we had only 50% of AB and 50% of CD, which means the concentrations of reactants and products was equal, or was the reaction endothermic? If the reaction was in the forward direction was endothermic, then concentration of the reactants would be more. Why? Because it is not favoring, endothermic reaction is not favoring the reaction in the forward direction. But if the reaction is exothermic in the forward direction, then the concentration of products will be more and then the equilibrium will be established. Right? So, but mathematically, you can use this value of delta G to calculate either any of these. If you can use this equation, whatever is given to you and whatever is not there, if you use these and relate them, you will be able to calculate the third. So, delta G also depends, yes. Another thing, we are only talking of the enthalpy now. Now, we also know that delta G does not depend only on enthalpy, it depends on entropy too. So, when you use the term of entropy and the value of entropy change, that would also affect the value of K. But this study is beyond the scope of your book right now. So, this would also affect the value of K. So, you can use this equation and we can estimate delta G from delta S and delta H. You can calculate delta G from delta S and delta H, and then you can use that value to calculate K. If once you have found out the value of delta G, then use this equation that delta G is equal to minus RT ln K and calculate the value of K. So you can use the value of delta G from delta H and delta S and calculate the value of the equilibrium constant at any temperature to get economic yields, that how much of yield do you want of the product, how much of enthalpy should be there, at what temperature would this reaction, if it is endothermic, what is the temperature at which the reaction would be feasible, and if it is exothermic, what temperature should you use. So it will help you to get a better yield industrially if you are carrying out the reaction. And if equilibrium constant, sometimes you go the other way. You calculate the equilibrium constant in the laboratory and you want to know what would be the conditions under which I would get better yield. So if equilibrium constant is already measured, then you can calculate the value of delta G at any other temperature. And at that temperature where delta G is minimum, that is the temperature that is, when delta G is negative, the reaction is spontaneous. So you will have to find out where delta G is minimum. At that temperature, if you carry out the reaction, you will get more yield of the product that you want. So that is how you can apply your knowledge of delta G to chemical equilibrium. So now, after having understood this, we'll solve a few numericals before moving on to the next chapter, that is chemical equilibrium. But we'll start doing the numericals from the next video. If you found this video helpful, please give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.